But I don't have your attention. I kind of got a little bit late here. Sorry, the camera took a little extra. All right, I got your homework, so I'm going to return at the end of class. I will not go over like I did last time. I'm very sorry about that. I normally end. I know you have another class after this. I'm really sorry about that. Look, I don't know what to tell you. Okay. Perfect. You made the record. Next slide. Next highest score was 85%. Very good. So you made the record. Highest scores I've ever had. So very, very glad about that. Hope this comes to grow. So, okay, come on, folks. All right, so if you haven't turned in your homework, just wait. Now I will accept it till 5. So if you haven't, just don't worry about it, right? Now, one of you has already used the take a picture of the homework thing. Now, I do accept that. I just have to be able to read it, so that's okay. Yeah, highest average I've ever had. So, and I'll make the homeworks harder. No, I'm not. I'm very consistent. I know, come on. I remember 4th grade, trying to do this. All right, so I take the old homework from last semester and I write over it a question that's roughly equivalent. And I think that's more than fair. And I know what people at MIT and Florida State, Northwestern, I know my equivalents there. I know what their tests are like, I know what their homeworks are like, and we're very similar. So you're not being cheated, I'm not making this too easy, you're doing well, so I'm very happy about this. Now, the homeworks are going to get harder, right? This last problem set, which took me until 3 minutes, that's why I was a little bit late for office hours. It's a long story, but the problem sets do get harder, all right? That's going to happen, but I mean, that's how things work, so do expect that. This next problem set, I got 1 or 2 questions that are definitely going to, be a little bit like, but this next problem set, which I will post immediately, actually, no, I'm sorry, I already posted it right before class. What I did was I took a lot of information about power plants, actual energy generating fuel burning. I didn't go nuclear, I went fuel burning. And so I have a lot of questions on this is the amount of energy it generates, this is the amount of gas that is poured out of the smokestack as a result. So you're going to analyze all that heat, all that work. And so it's a bit harder, but it's just how things are. But again, I'm very glad about this. I'm more than glad to give you all A's. If you all get above 90%, you all get A's, no problem. Statistically, very unlikely, but I mean, I will do it. I will do it. You deserve it. Of course, it won't be a curve, but if you all get A's, what kind of curve what do you want? A super A? So, planned that for a while, but anyway, so I do apologize for last time for going over. I will try not to do that again. And I do have to, like last night, I have to predict where I'm going to be in a week, and I just screw up sometimes. So sometimes I rush. Sometimes I will cancel. I'll just say, oh, sorry guys, I didn't get to number 10. Don't feel it. That's going to happen. Now, this next homework, actually, I think I gave almost every answer to the question in another question, or as a hint. I've done that, doesn't matter, as you rapidly figure me out. That's why you can, I saw this on Imgur, they showed this picture, right, of this person who took their cell phone, which of course you got the internet, took their cell phone and put it in a calculator's case. Go ahead and do it. You learn a skill. It's not going to help you on the test. Freaking open up the book right in front of me. Well, I don't do that, but it doesn't matter. It doesn't matter. It's not going to help you answer the test. It was this way when I took it. It's cruel, but it just doesn't matter. Also, when you get a test, and look, the first test generally doesn't go that well because you're still kind of figuring it out, figuring me out, and maybe that's kind of bad, but I mean, they picked me to teach the class, so I'm going to teach the best I can, so you have to deal with me. So maybe the first test won't go well. That's often the case, just to let you know. But you figure it out, and remember the first test is part of the grade.
What are like the typical averages?
What's that?
What are the typical averages for like?
Typical averages between, for the total, after all said and done, because who cares? I don't even know who said that, but too many people. So the typical average after all is said and done, especially remember the final is a very, very heavy weight. For those of you who have Ds, you can take the final, ace it, and get a B. It happens every semester. Every semester that's happened. And that's why that final has a heavy weight. At the end of the day, the averages are between 75 and 80%. And I will curve it roughly to 80%, and I treat all people equally. So I'm simply going to add a certain score to all of you equally. So you think about like, oh, well, how exactly do you curve? You get this. How do you manipulate it like this? Reality is, think about this. If you're trying to do this, you're helping the C's, but not the B. You're helping the D people get C's, which is what I want, but not helping the B's get A's. So you're punishing someone for having done better. That doesn't sit well with me. Hopefully it wouldn't sit well with you. So I give all of you the equal push, no matter what your grade is. So the typical average will be about a B minus, essentially, but of course we don't have minuses. Generally, I can tell you that my distributions are like this. This happened last semester. Now, obviously, you can figure out how that would, right? So it tends to be this way. This group here, missing half their homeworks. This group here, no more than one homework missing. Now, not because I not because I fixed that or I made that happen. You made it happen. Well, they made it happen. You didn't. I mean, you're doing pretty damn good. Okay, let's finish. Guys, I'm wasting way too much time because I'm going to end early. I just totally forgot. Anyway, all right, so I'll accept your homework until 5 o'clock today. I'm going to post the thing, and that's it. So we got to get started. Again, I just apologize for last time. You're anything early, getting your homeworks back. A's to Z's, it'll be a zoo, but it's the best I can do. And here's another way to tell you, it's not so very pleasant, but I'm forgetting something, but let's not worry about it. Again, thank you for you guys have been very quiet. You're the most quiet class I've ever had. I really appreciate that. Keep me from going crazy. So anyway, all right, now, I'm very sorry about rushing last time. Remember this is not unit, it's a change unit, and it's the sum of heat and work. And I was talking about work, but I went into this major rush so that you can answer numbers 9 and 10. And remember, inexact, exact, path independent, path dependent. And I mentioned that UPAC, before that, let me back up. I mentioned that work is force times distance. But I really like to think about gases because gases drive the turbine, that drives the alternator, that drives those lights on. And that's, now that we're going to have Chevy Volts and whatnot, and Nissan Leafs, that's where your car is coming from now. And that's going to be universal, really. Probably about 10 years, all of us are going to be driving what's cool vehicles pretty much. You're not going to have a choice. So I like to think about gases expanding. And it is, no matter what, the exterior pressure times the change in volume, and I prove that by thinking about a piston, its area, its force. Area times the change in distance becomes a change in volume. And then this is also force per area, so this is force times distance. Went over it last time, watched the video, I did upload the video. So anyway, and then IUPAC loves this little negative. It really is a pain in the rear, and one of you engineers did tell me that in baby thermo, you did not have a negative sign there. That should not be. IUPAC says it's negative. IUPAC gets to decide. I don't know why you guys are doing that. I think that's really weird. And maybe it's an American convention, probably, like we have inches and everyone else has millimeters and all that. But in this class, engineers don't get it wrong. I'm right about this, all right? So I don't know why you're doing that. I think that's nuts. So anyway, now. Path dependent, not path dependent, whatever. This guy's path dependent. Now we have two paths, two extremes of reality. Reality is always never quite clean, but whatever. Now, to get to the change in work, all right, because remember, what are the units? Units? Pressure times volume. Joules. We went over this on the first day, joules. But the value is 0, so therefore it has to be integrated. You got to integrate the sucker or it's nothing. It could be IVF. Okay, now it has meaning. Now it's not 0. It has units of joules, but it is 0 until I integrate it. And now this is path dependent, like we talked about before. And we had, oh, I hope you people on my right can see, we had reversible, and this is where I was rushing horribly. Okay, let's do reversible. That's when the exterior pressure is equal to the interior pressure. And get used to me just not labeling the interior pressure as being special. I'm just going to call it P. That means interior. It's going to come up a couple more times, a couple of other letters. And that will be, I'm going to add a slight differential. All right, and you know partial, that means zero. It's finite, but at the same time it's zero. It's very confusing. Partials are very confusing things. All right, so that means that the exterior pressure is essentially equal to the interior pressure. So that means that, oh sorry, I'm getting myself to a corner, is equal to P versus volume. And I forgot Boyle's or Charles's law, I already forgot that. Remember, you can't have anything below zero, there's no different pressures. And there you go. And like your homework, let's make this an expansion, that's kind of easy. I'm integrating, and integrations are always areas on the curve, there you go. All right, so that was one path, and then I told you that, this reversible is a fantasy. There is no such thing as a reversible process. And I can prove that in just, again, what Einstein would call a Gedanken experiment, a thought experiment. That is that if I'm always adding no pressure, then it will take me forever to do it. So there's another word for reversible. It means infinitely slow. So reversible processes are infinitely slow processes. Unfortunately, in chemistry, sometimes we have a word that has multiple definitions, like oxidation. Oxidation means burned, reacted with oxygen. It also means I took an electron out. Those are not the same thing, but they have the same word. So reversible means this. It also means infinitely slow. So the other path was irreversible. And that is more sensible, and there's nothing to write. It's just I changed the external pressure. So irreversible also means fast. This pen looks like it's already starting to blow chunks. And in the case of an expansion, I would lower the pressure instantly. If I lower the external pressure, I'm going to get an expansion. I don't know how I did that. I'm pulling out a plunger. I evacuated the room I'm in. That wouldn't be very smart, but that's what I did. And, of course, the plunger expands until the volume expands such that the interior pressure is equal to the exterior pressure, and then, of course, the piston stops. It's just sensible. Right, now on this next problem set, I have questions that, again, you have to kind of just use your senses to solve them. I'm not going to do every simple little thing for you. I want you to think for yourself sometimes. So just, you'll see. It's already posted. So anyway, two different things. And as I mentioned, reversible is most negative work. Okay, and this gets a star. This gets a star. Sorry, this gets a star. And that means you've got to remember this. All right, so that's important. I assure you it's on the first test. I don't quite know how, but it will be on there. It's too important not to know. All right, now we're going to have a couple more stars, even though I have 40 equations. What else do I want to say? Now, I proved on the homework set, hopefully you realize that if you go, these are expansions. If you do compression, I tried to convince you that this concept was screwed up. It was not. I don't want to give the answer because I'm still going to get some homeworks. But the answer was, I'm just going to go ahead and say it anyway, the answer was the areas were negative, but then IUPAC adds a negative side in front of that. And so that means that expansions are positive work and compressions are, sorry. Expansions are negative work, compressions are positive work. And now this is why this doesn't get a star. You can just figure that out. Let me write that down. Expansions are negative. Compression is positive. Okay, and we can look at that here. Let's see. Compression would have a negative change in volume, negative, negative, positive. Compressions are positive. Now you see this? I asked you this on the test. Are you going to try to memorize it? Don't. No, because I asked you to memorize this. I asked you to memorize this. You got a negative and the equation is on the cheat sheet. Even if you didn't, it's on the cheat sheet. Compression means that's negative. You can add in a negative. Even if you don't remember it, there it is on the cheat sheet, and that's positive. There you go. Just answer the question. You didn't memorize anything. There you go. 5 points. Very good. All right. So I'm going to make it more of a big deal of this, and then a little bit later. Do I have anything else to say? I don't think I. Yeah, I do have one more thing to say. Okay. Let's do a little bit more irreversible. Okay, so delta work is the integral of the change in work, the integral of minus P exterior, dV, and now that means that the exterior pressure is constant. Don't forget this. The definition of irreversible is expansion or compression against a constant external pressure. Someone asked me to prove that. That is the proof. It's just the definition. I can't do better than that. That means it comes out of the integral. dI, dF. And so this is minus P exterior delta V. Okay, and then in some snarky way, I will give you the change in volume. I don't know how I'll do it, but I won't always. So the initial volume is 3 liters, the final volume is 2 liters. No, I'll do it in some snarky way. I'll let you know what delta V is, but I'm not going to be that explicit. Just because, remember, cheap but not easy. Let's do reversible. I'm sorry about that. Can't help it. Now, here's what David was saying. Remember, the exterior pressure is the interior pressure. Now, this is a concept you've got to get used to. You've probably run into this before. I don't know if anyone's ever that explicit about it. That is that I can't just, this is changing with volume. It's a function of volume. So there's a V in here. Well, now you can't ignore it. You know, the integral of the change in x is x. The integral of x change in x is 1/2 x squared. They're not the same, right? So if there's a V in here, I need to know it, and there is. Minus n RT change in V over V. Vm over Vi. Sorry, no, I'm sorry. Like that. All right, and so this is very simple. And again, this will be on the cheat sheet, minus nRT, integral 1 over x, first, natural log of Vf minus the natural log of Vi. Can you simplify that? Yeah, that would work. Here we go. ln Vf over Vi. I heard it. If we have to do any class voting, which does come up, we'll do dual polls because it just doesn't work when I ask in class. Okay. So, 2 different equations, and again, I want to emphasize that this will be more negative than that, even if the answer is positive. And think of this, by the way, here's something I came up with at office hours. Think of it like a thermometer. As long as you're further down, you're more negative, even if you're above 0, right? So, again, the way to think of it. It just comes out that way. It's kind of a miracle, but there's really no setup, a realistic setup. You know, if you violate the rules of Mother Nature, anything can happen, but that's obvious. So, any realistic set of numbers you can ever use, this will always be more negative than that. All right, so again, review, this is path dependent. I have something else that's path dependent. We're going to talk about heat. Now, these are something that's path independent. So here's the thing. This is why this keep hearing you, little mouse. Anyway, so what's kind of interesting is that when it comes to changes in U, as we move on, won't quite get there today, I can actually analyze changes in U as though it's a reversible process. No matter what I'm describing, a car engine, a power plant, a nuclear power plant, a monkey, it doesn't matter. I can always analyze U as though the monkey's doing its work reversibly. And that's often a lot easier than irreversible. That doesn't maybe quite look it right here, right now, but anyway, you get my point. Just previewing. Okay, let's do heat. Okay, heat is Q, but of course it only exists as change. Heat Heat is a change of heat. And let me actually look at my notes. Rambling on. I don't have much to say. Heat is heat. I'm going to have to kind of give that one to you. Now, we're going to relate heat to heat capacity, by the way, so that we can talk about, well, I add this many BTUs. I'm not going to use BTUs, okay? I hate BTUs. British, Irish, by the way. So I'm going to use joules, but again, I'm burning a candle. And in time, we are actually going to talk about burning octane. That's one of the questions that we'll do later on. So I can take a chemical process and talk about how much heat is actually generated. But for the most part, like on the present homework set, I'm going to say I added 15 megajoules to the gas inside the turbine that drives the alternator that gives us that. So there's not much to say about it right now, although it'll be interesting when we get to heat capacity. Now there's a sign convention. So again, on the questions, I just say, I added 15 megajoules. So I do, the next problem set is on power plant, so everything is in megajoules, by the way, because that's actually real. Those are real numbers that I have in there. Okay, now positive heat is heat in, and negative is heat out. Okay, so there you go. I don't have much else to say, really. So if I say plus 15 megajoules, that means that I have a turbine and it's sitting on a roasting fire. Heat out, I have a Coca-Cola and it's in the fridge. So there you go. And I'm not going to say more about that because it's actually one of your homework questions to really think about what that means. I'm going to talk about a gas heating and cooling in a cylinder, expanding and contracting. And the question on your homework is you're going to put your hands on it, you're going to tell me whether it's hot and cold. And it sounds easy, but trust me, I bet you'll get a little flummoxed, but then you'll figure it out, and then when I ask the same thing on the test, you're okay. So, so the mnemonic. The mnemonic to remembering all this are, remember, compressions are positive, expansions are negative for work. Heat in is positive, just I have nothing better to do than just say that that's how it is. So there's a mnemonic. Energy bank is what I call it. Let me write that down. Energy bank. Because, all right, now here's the point of this. I have, as on the present homework, 950, see, I wrote it last night till 3 in the morning, 951 moles of nitrogen gas expands. That's how question 2 on your present homework begins. And I'm saying, what's the heat, what's the work, and what's all blah, blah, blah? What is all this stuff? All right, now, expansion. Expansion is negative work. All right, now, if you do the calculation, you get positive. You blew it. Now, you know that, so you got to remember that stuff. Now, so when it comes to doing your tests, when you get an answer that's clearly ridiculous, know that you've done it wrong and fix it. Right? That's one of the best things about helping with grades is knowing when you made a mistake. Well, that's true in general. I married the wrong person. Oh God, that was very extreme. I'm sorry about that. So, anyway, all right. So knowing when you've made a mistake is half the battle. The energy bank it's positive to store energy. And that's obvious, especially at your age. You need to be saving, you need to be storing. You get to be my age, you get to spend a little bit more. I bought my first house recently. Hey, I'm going to buy a cat. So, because I've stored a lot of energy. Yep, I've done that. So, you can't imagine the real way. Anyway, so storing energy. Now, the heat is easy. Now, heating something up clearly is putting energy in there. That's brain dead. A 5-year-old can understand that. Compression. Okay, that's a little bit harder, but now the way the book says it, I haven't looked at the new version of these. I based my notes on the old version, but they're probably the same. If you think about it, if you're compressing something, you're imparting a greater ability at a future time to expand. And so that's energy storage. That's how the book says it. That's about as good as the ways I think I can express it myself. Now, it turns out that negative work is actually good work. And I'm going to show examples later. It's a little hard right now to explain. But when you build a car, because we're going to talk a lot about car engines in this class. And it turns out that the way a reciprocating motor works, you've got the piston that, that you got this thing that's expanding and then contracts and expands. The expansion is very good at driving what's called a power stroke, which is a camshaft, and the piston does this, but it does it on the expansion, the negative work. It just turns out when it comes to engine design that expansions, it's easier to design a car to be powered by an expansion than a contraction. It's significantly easier. It's just a practical thing. But it has to do with the fact that chemical reactions tend to get hot and not so much cold. Both happen, but more reactions get hot than reactions get cold. And we're going over that. Because of that, it's easier to design an engine where a piston expands and that provides the power stroke, as opposed to gets cold and provides a power pull. It's a power push, not a power pull. So negative work is good work. That is how we design car engines. That's how we design turbines. Not positive work, but negative work. So anyway, that's coming up. Just want to get you used to these sign conventions. Let me recap just about everything. I know we've only been doing this for 2 days. Again, that U is heat and work. I started with this. But now, these I cannot say Q equal, I can only say the change in Q is. I can integrate it, and this little partial turns into a delta, but I never have Q equals in exact. U is exact. By the way, I added 2 handouts on exact versus inexact, because I kind of screwed it up not talking about it. I also added a little bit about the equal partition theorem. So there's handouts on the web, look for that. Degree freedom. Okay, remember equal partition theorem gives me this, and then I can talk about its change. So this equal partition theorem is really the fundamental part of thermo. This is the ground floor. And then we talk about how things change, because things changes how we build things. Remember degrees of freedom for argon, xenon, helium was 3, because it can move up, down, left, right, forward, and backward. 3 dimensions. So the internal energy of helium, xenon, is 3 times RT. For CO2, N2, O2, there are linear molecules. It was 5 halves because it can rotate 2 different ways. It can do this, it can do this. Right, but it can't roll, cannot roll, so that's 2 more degrees of freedom. And then nonlinear molecules can do 3 different types of things, 3 different rotations, just because we, again, same reason, 3 dimensions, 3 rotations, just how it is. So methane, everything else aside from CO2 and N2 and all that have 3 RT of U. So don't forget that. Now here's another thing, and I don't think I brought this up yet, and I don't know why. At constant T, the change in U, who wants to venture a guess? Now I want to point this out, this is U. Now, I don't think a half is going to turn into 0.4 anytime soon. That would be bizarre. R is 8.314. T's, whatever, you can change. But if it's not changing, then U is 0. There you go, very good. U is 0. And always units. If you forget units, I usually take a point off, but sometimes I'm pretty forgiving. Now, this gets... Sorry. Now again, now this is, oh God, this guy's important. I already put a star by this one, but it's another one that you definitely need to remember this. Now here's another example. You know this, therefore, as you just did now, you figure out that. You do not try to remember this. And you don't remember this either. This is automatic. See, you know this. And by the way, this is on your present homework set. You memorize this. But instead of remembering 4 equations, you remember 2. The 2, this one gives you that, this one gives you that. There you go. 4 equations for the price of 2, not that. That you can do. That's that. And by the way, this is very much on your present homework. So what happens is an isothermal process, and again, as I've said many times, you are very good at logically understanding what things do. It's not going to happen in 346, and that sucks, but for this class it is true. You know, if I compress a gas, does it get hot or cold?
Hot.
Hot. Your gut says that, right? Well, for one, it's true. Your gut, you know that compressing a gas makes it hot. It just feels right, and it is right. Not gonna happen in 346, but it does happen here. Okay, but it's isothermal. This is an isothermal process. Again, this is another one of those paths, by the way, that use paths independent. Now I'm getting there anyway. So if the gas wants to get hot, and I'm going to say that the gas is in a metal cylinder, look out for that. When I sometimes will not often say temperature is constant. Sometimes I'll say the gas is in a metal cylinder. You know metals will shed heat very easily. So the gas compresses, it gets hot. What does heat do? All right, I've done work. I've done positive or negative work.
Cool down.
I compressed, positive energy bank, I stored energy. Now that means U has changed, but I'm saying U hasn't changed. U hasn't changed. So this guy does the opposite. All right, so positive convert negative heat. Of course, it's negative. You have that right here. Compression again is positive. Positive times a negative is a negative. So the heat is negative. Now, let me just go ahead and answer the question on your present homework. I touch it. I have just compressed the gas in a metal cylinder, and I'm touching the metal cylinder. Alley or, ooh, that's cold. Which one? Hot. It's hot. That's right. Heat's coming out. The heat is coming from it to me. You know heat going to you is you're on fire. Not because you look good, all right? Because you're on fire. Oh my God. All right? You're Justin Bieber, but better. All right, anyway, so, I didn't mean that. Let's see. All right, now I gave you the things for work. I've already done that. So, yeah, all right, so then there's the equation for work, right up here. And heat is heat, and at constant temperature. All right, so homework. You're going to calculate work for the power plants, and then this is what gives you heat in almost every case. Until we get to heat capacity, which we will do next time. Okay, so let's switch subjects. I'm sorry to introduce too much at once. If any of you have a Post-it note, you could do me a favor and write on there to Circuit Boy, please erase the dry board after you're done. Because it's kind of annoying. I was told I came here to erase the dry board. You noticed me, it's on the film. I erased the dry board when I'm done. Circuit Boy's not doing it, it's really annoying. Anyway, I'm just a little annoyed at that. Okay, enthalpy. Okay, this is a really neat thing. You know enthalpy is H because you had it in high school. And if somehow you didn't have chemistry in high school, which would be pretty weird, you had it in freshman. And, okay. Let me back up a little bit. Okay, at constant volume, what is the change in U?
Zero.
What's work at constant volume?
Zero.
Right. Even if remember I said this last time, even if you're pushing on something, if it's not moving, you're not doing anything. Even if you're exerting yourself, that's irrelevant. Internal energy is heat. Okay, that's all fine and good. And remember, we power the planet by heat. Everything comes from burning, except solar power. Oh, by the way, this is wonderful. I was reading the other day as I was collecting, I'd really like to give you real numbers. I can just say, oh, a mole expands from 22.4 liters to 25. I can come up with that. But instead, and I used to do that when I was just starting, but now I spent a good bit of last night looking up realistic numbers on what do power plants actually do so that you have realistic examples to work with. God, this was sad. Any of you have any idea how much of our power is produced by solar? What percent?
About 10, 2, 4.
1? 1%. I read it last night. Show me a different source, but it was 1%. So that blows. And our use of energy is expanding tremendously. Not the United States. We're going to double our energy uses in the next 40 years. To be perfectly honest, it's China, India. And a lesser extent Brazil, their energy consumption is going to skyrocket to an unbelievable extent, and there's no way it's not going to happen. So our energy consumption is going to go up about a factor of 5. Very little of it's going to be solar. That blows, but it's true. So solar is energy not from heat, but 99% is from heat. Now, here's the damnedest thing. All right, in high school at freshman, what was heat? Was internal, did you even learn about internal energy? No. You learned about enthalpy, and enthalpy was what? If I touch the thing and enthalpy is negative, it's exothermic, it feels hot. Well, no, hold on a second. No, that's changing U. You didn't learn about U, you learned about H. But I'm telling you, U is heat, not H. But volume has to be constant. You see? Part of my class is correcting a lot of lies we once told you. And that sucks, but it's true. So let's talk about enthalpy. Now, you've learned that enthalpy was heat, and I'm telling you it's not true. It's U plus PV. And again, we don't talk about U, internal energy, in freshman or in high school. But this is what it is. It looks like a lot like G is H minus TS, doesn't it? They have a lot in common, by the way. We're getting there. Actually, I'm getting there today. Okay, now when it comes to, there's this concept called natural variables of a function. It only exists in thermo. It's not a mathematical concept, it's a thermodynamics concept. And let me tell you that to understand the function, and so forget about this for now, to understand a function, you want to see how it changes and what's changing it, and that tells you how it works. And so let's talk about the change in H. What am I doing on time? Okay, just got a few minutes left. Okay, that's the change in U plus the change in PV. Now, we went over this on that first Friday, change in U plus P change in V plus V change in P. Get used to this. You've got to be able to do this. Seems very simple. It is. Let it be simple and don't ever forget it. How to do these changes, all right? This is going to come up an unbelievable extent, here to here. You're going to see a gazillion examples. Okay, now U is the change in heat plus the change in work. And let's not forget these other terms. Because this pen is shot. Okay, now, again, U is path independent. My paths, as you've learned so far, is reversible versus irreversible. Now, again, there's not a lot I can do with Q, so I'm just going to keep Q as it is. But I'm going to choose to go down the reversible path in terms of the work done. Why? Because I can. It doesn't matter. Sorry, I think I can see something you have trouble seeing. And that's minus PdV. Oh, plus PdV. Well, that's a problem. PdV. Well, clearly, BAMO is equal to heat plus dVP. Okay. Now, here's the crazy trick. This guy is heat, and again, heat's important, and that's the whole exothermic, endothermic thing. That is exactly that, just like you knew it. I'm just telling you, it's not enthalpy, it's internal energy, but volume has to be constant. Now, if I hold something constant, how can I make H become Q?
Constant pressure.
Constant pressure, right, at constant pressure, the change in H is the change in heat. There you go. Now that's the concept you did learn. So why did we lie? Okay, now you're in organic class. How many times did you do a reaction in a fully enclosed vessel? Never? You sure? You remember? I remember. I remember lots of stuff. Did you ever do a reaction in an enclosed vessel?
No.
Maybe you had a Schlenk line. Maybe, I don't know. I'm afraid one. It used to be much worse, by the way. Illinois Tool Works gave us $5 million to fix up the organic lab, by the way. That's why it's as good a shape as it's already in. You should have seen it before. The answer is no. I don't know, again, but doing a chemical reaction in an enclosed vessel is the most unbelievably dangerous and stupid thing a human being can do. Because most reactions tend to get hot, and we're going to see why in a little bit. It has to do with entropy. So most reactions tend to get hot. Let's say you add too many chemicals to the pot, and the chemical reactions get hot. Now, hot often accelerates a chemical reaction as well. So you've got a lot of bad things happening. You've accidentally added too many chemicals, you have it in a solvent. The solvent's job is actually to keep the chemicals cool, but they're not going to get cool because you added too many of them. And they're going to react faster because it's getting hotter and hotter. Eventually, the solvent boils. Now you're dead, right? Because if you're in an enclosed vessel and a little small volume of liquid turns into a gigantic volume of gas, roughly a gas, the volume of a liquid is 1% the volume of the same liquid in gas form. That is the definition of explosion. Right, now, so one of the questions on your homework, I'm answering it right now as well, is you don't, it sounds so weird. That's fine, that's good, you should do that. Almost nothing occurs at constant volume. For one, am I doing this at constant volume? Am I in a cage? Does the earth got a metal box around it? No, I'm not in a cage. I'm in a room, but there's a door, so I'm not at constant volume. I'm at constant pressure. And chemical reactions. Do we do them at constant volume? Sometimes, but in things called autoclaves, sometimes we do things at constant volume, but it's rare because it's unbelievably dangerous. We almost all do things at constant pressure. So, sorry, there's a question? Question?
I was just trying to ask, you know, when you're talking about quantum,
Uh-huh.
and how they kind of happen in the cage.
Yeah, quantum mechanical
That's
things.
all different.
The funny thing is that, so the question was, but he said quantum mechanics occurs because things occur in a cage. The cage can take many different forms. One form of the cage of a hydrogen atom is the fact that an electron cannot overlap the nucleus. That's its cage. But it doesn't require an actual cage. Right, so you can still have quantum and quantum confinement and energy levels without necessarily a box around. Sometimes the box can be inside. And so that's why almost all things are quantized, whether they're in a box or not. The box can take many forms, but you're covering that. So anyway, so yeah, we can only all things at constant pressure. Constant volume is rare, and that's why we simplified it. We simplified it and told you enthalpy was always heat, because almost nothing occurs at constant volume, so we just pretended that it didn't happen. It's not fully true. Sometimes we do things at constant volume, rare, but it does happen. There are chemical reactions, especially in my field. Sometimes people get these really thick plastic Teflon, they look like batons, fill them and close them and put them in microwaves. Sometimes they're made of metal. You have machines that like rivet them together because it is very dangerous. You heat them to fantastically high temperatures and pressures. You wait a couple of hours for them to cool down. You open them up and there you go. In which case the heat was never the enthalpy, it was internal energy. So there you go. Okay, well, I promised I would end a little bit early and to hand out your homework. Real quick,